All right, so I was asked to just give a quick summary of what we've seen so far. It's actually probably good. So let me backing up to the very start. The grand challenge is that we have to find some question to ask in the asymptotics of flat space. What you can call flat space holography. This is another way of talking about it. Lots of equivalent ways of talking about it. But one way or another, there's some data that labels the scattering process, like the energy and momenta, the form momenta of the particles. There are lots of ways of labeling the actual variables that the scattering amplitude depends on. Maybe they're momentum twistor variables or they're Mandelstam variables. So we have lots of choices for how to label them. But once we figure out the space where they live, we have to find a question in that space. And that's the non-trivial part. How do you find a question in these seemingly boring, arid spaces, like the space of n null momenta? What the hell are you supposed to do in the space of n null momenta? Or the space of n momentum twister? Or the space of all these Mandelstam invariants, or these xij? That's the space. That's the space where the amplitude lives. Our program is to try to find a question in that space whose answer sort of inevitably gives rise to these complicated, beautiful functions that we are going to interpret and think of as scattering amplitudes, which have to have all these properties. They have to have singularities and factorization and all sorts of properties that we normally ascribe to local and unitary evolution in space-time. The entire point here is to try to find some way of getting to the same answer in a different way, by finding a different kind of abstract question in these kinematical spaces. Okay, so yes.
Nima, can I just ask a sort of general question, which shows maybe I haven't quite understood? You have endpoint amplitudes, but when you look at an S matrix, you have to select so many to be incoming and so many to go outgoing, right? So there's crossing relations. And then the question of what is the causal time relation is selected after you do that decision.
Oh, sure.
There's many solutions according to how you partition this, right?
Sure, indeed. In fact, this is if you, I mean, I would read this comment the other way. There are lots of early indications in the structure of amplitudes that there's something in them beyond the conventional picture of evolution in space-time. And crossing is one of the very early ones. You know, we've become so used to it that we immediately say, oh, forget about the fact that there's some in and out. We just imagine there's one function, and then we get to continue who's in and out depending on the sign of the energy to interpret it as an in and out process. But it's fascinating that the basic thing doesn't want to be thought of as an in and out process, that the more basic object is not an in and out process. It's something that just democratically depends on all the momentum. And it's our desire to interpret it by making the momenta real in Minkowski space. And I remind you, only with real momenta in Minkowski space is the sign of that energy means something, so that we can talk about past and future, in and out, and then it has a conventional unitary interpretation.
Right, but when you try to map into the sort of TX space, that's a multi-map according to how you do that selection.
Well, actually, no, because yeah, I mean, first of all, of course, I mean that it's multi-map in the sense that it's 2-to-1 because it's quadratic in the piece. But there's a much bigger problem, and in a longer series of lectures, I know it's hard to imagine getting longer, but I would spend quite a bit of time on this point and I think this is an important point because it's the deep reason why the S-matrix program failed. I really think this is the deep reason why the S-matrix program failed, is that the whole idea of the S-matrix program was that the amplitudes would have singularities, and the only singularities they would have would be the ones that were necessary for unitarian, right? So in other words, you have to believe that the only singularities the amplitude has are the ones that are forced to be there because of particle production, roughly speaking, right? Now, if you think about it for a second, that seems a little that seems, I mean, it seems a little bit crazy, because once you go off into the complex plane, general momenta, why the hell would the only singularities of the amplitude care about real Lorentzian momenta? Only for real Lorentzian momenta can you interpret all singularities as having something to do with particle production. But we already see, because of crossing and lots of other things, that you certainly don't care about in and out. You don't care about some of the most basic facts about Lorentzian physics. But even beyond that, already at tree level, it seems a little nutty to think that Lorentzian physics can cover everything. There's a very basic fact that if we look at the Mandelstam invariance at 4 points, we can't even cover all real values of ST and U with Lorentzian momenta. Never mind complex values, right? We can have S positive, but T and U both negative. We know we have to have S plus T plus U is 0, but we get one pattern where one is minus, or one is plus and the other two are minus, but we don't get the other pattern where two are plus and one is minus. So that seems a little, weird to think that we're going to learn everything about the behavior of this amplitude everywhere in the complex plane by knowledge of what it does in Lorentzian signature when we can't even cover all the real invariants with the Lorentzian signature. And everything that I was talking about in the first part of the lectures, this imaginary experimentalist with their finger on the Mandelstam dials and so on, in fact, none of that could actually exist in Minkowski space. The most basic thing, even at tree level, before we get to loops, the fact that we have these poles that S and T goes to 0 and so on, those are inaccessible in Minkowski space. I can't send S to 0 in Minkowski space and see that damn pole for the phi cube theory. So I can, so that's really interesting. That already shows that to the extent that we know the singularities of amplitudes matter, we're not even capturing the ones at tree level in Minkowski space. So that's another indication of why, if we're going to play this game of looking for something to determine the S matrix, we have to be more adventurous. We have to think about some other structure that's going to give us an answer that will then interpret ultimately in Minkowski space, but it's very unlikely to be fundamentally based in Minkowski space. There is some indication that whatever's going on, it likes split signature. It likes 2,2 signature. And there's many, many indications of that. But one of them is simply that in 2,2 signature, you can get all the real values of Mandelstam invariance without a problem. Okay, and you know, it's a more Lorentzian signature anyway, more democratic between time and space. There's all kinds of things interesting things you can say about 2,2 signature. But I think that certainly all the things that I've been talking about in these lectures and all this business about geometry, positive geometry, blah, 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 all the stuff where the geometry lives, like let's say this icosahedron, we have to assume that all of these x's could be positive. That's impossible in Minkowski space. I can't make all the x's positive in Minkowski space, but I can make them all positive in 2,2 signature. So somehow all these geometries live in 2,2 signature. And you know, maybe optimistically, we can think that if there's some kind of structure in 2,2 signature that's a counterpart for amplitudes to Euclidean space as the place which fundamentally determines correlation functions. But there is something out there. Clearly, there is something out there. Who knows what it'll all mean in the end? But there's no doubt there is some structure in 2,2 signature that knows a lot of hidden things about the structure of amplitudes. Okay, so anyway, it was an excellent question, and I hope you forgive the longish answer. But
thanks very much. Very interesting.
Nima, there was one question in the chat.
Yes.
About, I don't know if you're going to get there, about A coordinates versus X coordinates.
Ah, yes. I'm not going to get there. Let me say one thing. That just sorry, but what is the question?
Eden.
Yes, everything that we've been talking about has been about the A coordinates. There's a lot of interesting things about I mean, I'd like to understand the X coordinates better. There's a very special set of X-like coordinates that we like very much. That we call U coordinates. That are a special kind of X coordinate which are, however, in bijection with the A coordinates. There's as many of them as there are A coordinates. And they have a lot of interesting properties, but they're only defined, as far as we know so far, for the finite type cases. But no, I'm not going to say anything about the X coordinates. I should say one point, which but maybe I'll say this now. I didn't. It was an oversight not to say it before. So when we wrote, can you guys see my screen now? Hold on. Let me. I don't think so. One second. Sorry. Whoops. Okay. So when we we talked about this basic, very nonlinear mutation relation, right? xv prime equals the product of all the w's into v of xw plus the product of all the w's out of v of xw. But closely associated with this is some linear relations, and these linear relations are we do a lot of linear algebra with them, and they're much easier, and they're also closely connected to G vectors and a lot of other things. But I just want to tell you what they are. What are these linear relations? Well, we have a mutation. This is a mutation. It's God-given, but associated with the mutation, we have actually a pair of linear formulas, which are so if I call these variables capital X. Well, maybe to be consistent with my previous notation, maybe I should have, I've been inconsistent with notation all over the place, I apologize. But anyway, let me call the cluster variables for this exercise little x. So I have little x v prime is the product of w into v little xw plus the product of w's out of v of little xw. Then, associated with this mutation, there's actually a pair of linear formulas, which I will write the capital variables to be the things that are everything is linear. So it's xv plus xv prime is equal to the sum of all the w's out of v xw. That's one, or it's the sum of all the w's into v of xw. So this is two relations. And the relation between these two things is a very simple and beautiful one. The lingo is that it's tropicalization. But the sort of simple idea is to imagine, just to get an idea where it comes from, imagine that these variables, imagine that these x's are the exponential of something, or the exponential of some capital X, or maybe with some parameter, some t capital X, and ask what happens as t goes to infinity. See, as t goes to infinity, the product of the variables here will turn into, so if I have xv times xv prime, well, this is going to go like e to the t xv plus xv prime. Okay. On the other hand, I will either I'll get the product of all the w's into v of xw, and this is going to be e to the t times the sum of all, again, the sum of all the w's into v of xw, and the other term will be the other way around, right? The other term will be e to the t, sorry, these are the little x's, w out of v, capital XW. And the point is that as t goes to infinity, one of these two terms is going to dominate. We don't know which one. One of the two terms is going to dominate. And so the formula that we'll end up having between these, just for the moment, for simplicity, imagine all these capital X's are positive, okay? The formula we'll end up having is that xv plus xv prime is equal to the maximum of whoever is the bigger of the sum of xw one way and the sum of xw the other way. Okay, so this formula is also God-given. There's no choices being made, and this is known as the tropicalization of the mutation relation. And it's something you can do with any algebraic relation. Wherever you see a product, you replace it with a sum. Wherever you see a sum, you replace it with a max. And it's always thought of in the same way as imagining that there's some limit with an exponential parameter, taking the parameter to infinity. Now, but one of the cool things is that the G vectors satisfy these relations. One of them, I mean, I have to make a choice when I satisfy one of these relations. Which one depends on it depends on what your choice of initial cluster is. Okay, but the G vectors satisfy that x. Now the G vectors for x plus the G vector for x prime is either equal to the sum of the w's into v of the G vector for xw, or the other way around. Right. So this is extremely convenient, and so you can do a lot of things linearly. On the other hand, the essential nonlinearity of the problem is reflected in the fact that which choice is made depends on initial cluster and depends on the mutation that you're talking about. So this sort of tropicalization is about taking this very nonlinear structure and breaking it up into pieces that are making it as linear as you can, making it into something that's piecewise linear. Now I mention this only because all the relations that we were talking about in our Gauss's law story, in the walk story, all of that stuff were precisely these things that look like xv plus xv prime minus x, blah blah equals. Now then we put them equal to a constant, but this stuff, the stuff on the left-hand side, are the tropicalizations of mutation relations. And the claim is that let's say you just chose an initial cluster, you get all the G vectors, then you can take any pair which are mutable, one can be mutated to each other, and one of these two terms will make the relation true as a relation between G vectors. Okay. Should we start?
Yeah.
Oh,
Okay, great. So okay. So now this is towards all loop amplituhedra, icosahedra, cluster polytopes, but for the phi cube theory. And before getting to all loops, I want to go back to one of the basic motivating examples of quivers, and that's the cluster algebra associated with surfaces, associated with triangulations of surfaces. And even before going to the cluster algebra, let's just go back to thinking about our kinematic space. So remember, to begin with, we talked about these Feynman diagrams, and we quickly realized that we could more nicely even think about them as triangulations of a polygon, right? So we can dually think about Feynman diagrams as these triangulations of polygons. Okay, and doing that, our natural propagator variables became these chords, or we could call arcs, in this triangulation. Now, if we just keep going with that, then we'll get more interesting spaces. So for example, what will things look like at one loop? So let's say I draw this sort of simple one loop diagram. What is the dual of this diagram? The dual of this diagram, well, I'd put a point in the middle there. So this is sort of old hat to most amplitudologists, but in case there are some people still on here who are not. The dual of this diagram, you put this point in the middle to correspond to a loop, and then you draw all of these guys. So that's what you would be drawing instead. Okay, you just draw this. And how can you think about that in terms of a surface? Well, I mean, that's just, so what would I do for an end, for endpoints? How do I think about endpoints? Well, let's say I'm doing one loop. If I'm doing one loop, let's say even 6 points, then to say that there's a loop, I actually have to sort of put a little hole in there, and then the rest is the same as before. I can triangulate. For example, I can triangulate like this. Okay, and that just corresponds to this ring diagram, the dual of this ring diagram. 4, 5, 6. Okay, so again, sort of most obviously, if you just put the points in the middle here and connect them, then that's the dual diagram that we get. But we can do other things. So really what we're doing when we draw one loop diagrams, there's a dual of some triangulation of this hexagon, but with this little hole in the middle, or if you're fancy, you call it a puncture. So with a puncture in the middle. So you would draw, for example, this is also one. You don't have to make them all go to the puncture. You can have something like this. I don't know. So, all right. And so what does that diagram look like? Well, it's clear what this looks like. This is something like a 4-point with a loop in the middle and other things sticking out. So we could keep drawing the, I'll just draw this last example. So it's something like this. Okay, so it's a diagram that has some tree level propagators and has a loop on the inside. Okay, so it's clear that if we're talking about loops, if we're talking about if we're talking about trees, we are talking about triangulations of a polygon. But if we're talking about loops, for example, one loop, we're talking about the triangulation of a polygon with a hole in it, with a puncture. If I'm talking about two loops, L loops, let's say planar L loop diagrams, it's just a triangulation of a polygon with L punctures in it. Okay, and we can go beyond the planar limit if we draw these diagrams on surfaces of higher genus. Okay, so this is just a very basic correspondence between Feynman diagrams. Even beyond the planar limit, I can draw them on higher genus surfaces. When I draw them there, I can draw their duals. So I have correspondence between triangulations of surfaces and Feynman diagrams. Okay, so that's a very, very basic connection. Now, this is why, so given that we've seen already at tree level that there is a connection between the cluster algebras of the triangulation of surfaces with the icosahedron and all the rest of it, then a natural place to start to wonder what's going on at one loop is to ask, what is the cluster algebra associated with the triangulation of a surface with a hole in it? Okay, so to begin with, let's just see, even at one loop, let's just see what the quiver looks like. Okay, so here's an example. Let's say I have 4 points. I put this guy in the middle, and now I'm going to triangulate. So there's one simple triangulation. And now let's do the same rule that we had before to get a quiver. Remember, the rule is that we put a dot in the middle of all of the lines of the triangulation. We have these ones on the outside that we don't really care about, but I'll just put them in anyway. And then we draw these triangles inside each one of the triangles, all oriented the same way. Okay, so tuck, tuck, tuck. And okay, so if I look at what's left, just with the blue dots, you see, I get this nice quiver. All right, it has okay, and I leave it for you as an exercise to work out that with some mutations, you can turn this into a picture for D4. Okay, so this is an exercise for you to show that you can actually do some mutations on this to turn it into actually any orientation of this quiver. So in other words,
the arrows be counterclockwise, or
sorry?
should it be counter?
Oh, I'm sorry. Yeah, I drew them backwards. Thank you. Yeah, but the point is that they all go around. Okay, so thank you. Okay, so this is an exercise for you. Just at the level of the picture, even you can see that by doing some mutations, you can turn this guy into that guy. I could, if I really wanted to spend longer talking about DN, there's some small annoyances about sort of degenerate Feynman diagrams or the duals of diagrams that would involve bubbles and tadpoles, it's very simple to talk about, but I think I won't talk about that. But what I told you was self-contained. I mean, this is certainly obvious from this picture, which is clearly, I mean, the Feynman diagram is that one. From this picture, you get that quiver, and from this quiver, you can see that it's actually D4. And in general, you can see that it's actually Dn. So you see, that's really cool that we can see that just from thinking about what the diagrams look like, it's clear that if one loop has to do with anything, it will do with Dn, just because the corresponding quiver is the quiver of Dn. All right, so that's okay. And that's the connection that I told you about already. It's true. There is a direct connection between this Dn cluster polytope and the one loop integrand in this phi cube theory. Okay, so with that motivation, let's go on a little bit, and let's now talk about two loops. Let's say. So here's a picture. Say 4.2 loop, and so here's a triangulation. I don't know. Okay, I hope it's clear that's a triangulation. Everything here is a triangle. Okay, let's see what's the dual diagram, just to see that it's a two loop diagram again for the last time now. So it would look something like oops. Okay, so in here you see the double box. Okay, so there's the double box two loop diagram. Okay, very good. Okay, so great. It seems like we know what we're doing. So all we have to do is study the cluster algebra of surfaces. Surfaces with punctures, with many punctures, with many L punctures. And we're off and running. Okay, but something new happens. Something new and a little funny happens beginning at two loops. Okay, and so in order to see, it's again, it all has to do with our picture of the kinematic space. It's really remarkable how much these things have to do with such simple basic points. You see, we want to say that here, like as we just saw in this example, this variable, like the one that I was associated with this, I want to think about, this is a loop variable, right? This is some loop variable. It's one of the two, it's one of the two loop variables. Like in this example, on this left-hand loop here, this variable was that part of the loop. Okay? And when we draw this picture, when I draw the picture of the double box like this, great, no problem. I can even start with that picture. I can go backwards. I can go backwards and I'll just get the one that we drew above, right? There's no ambiguities. Everything is fine. So everything seems okay, but from the perspective of this picture of the surface, it isn't okay, because there's actually many loop variables of this sort, and they're different from each other from the perspective of the surface. So let me draw these guys here. So this is 1, 2, 3, 4. Okay, there's the one that I drew, but there's also one where it winds around the other hole, the other puncture, and it comes back to where it starts. And from the perspective of the surface, these are two different variables. And of course, I can keep going. I can wind around arbitrarily, right? So I can start here, and I can wind around all I want before finally ending on that puncture. Okay. So, and these are unavoidable. If you think in terms of surfaces, these are really different from each other. And remember, the whole point, the whole sort of magic of this cluster story is it tells us that different diagrams are related to each other, and you can mutate one to the other. And what happens if you do these mutations is that as you keep going, you end up coming back not to the variables you started with, but some of these wound versions of the variables, and you just keep on going forever. One formal way of describing this is that once you, in the surface with two punctures or any number of punctures, there's an action of the mapping class group. That's the fancy name for it. But all this means is that I can take these two punctures, I can do anything I want, whatever they're connecting, but I can imagine I just take them, I sort of take them out, I rotate them, and I put them back in. And I can rotate them any way I want. That doesn't change what the actual surface is doing. I put them back in where I took them back out. But if I do that, it can wind these arcs around by arbitrary amounts. Okay, so that's our first infinity problem. So remember, I told you generically cluster algebras have infinities, and these surface cluster algebras, this is the origin of their infinity, is that I can leave the surface so it looks exactly the same, but I can do this mapping class transformation on all the punctures, and that can wind up all of these, all the variables that we want to associate with loops. And so that means we naively have infinitely many variables. We don't know how to think about a polytope. We don't know how to think about this picture of the space-time or the walk or any of the rest of the things that we did before. Okay. So I want to tell you what the strategy is for dealing with this, and maybe I'll say a couple of general things before starting. One of them, and this is I think really quite remarkable, is that there is something special about from the perspective of physics and Feynman diagrams and so on. Certainly, these surface cluster algebras are special. They're special because they're the duals of Feynman diagrams, and we care about them. But it's also remarkable that they're special purely from the cluster algebraic point of view as well. You can ask the question, which cluster algebras have the property of being of finite mutation type? That's what I mentioned before, that the quivers come back to themselves, even though the variables might keep on going forever. And it's, I think, an amazing fact that the ones that are of finite mutation type are exactly the associated with triangulations of surfaces in general, not planar. Surfaces of any genus I think that is just amazing that that this thing that we care about so much from physics is also a natural answer to an intrinsically cluster algebraic question. There are some exceptional cases. I forget, maybe 11 exceptional cases. But basically, all the finite quiver type, all the finite mutation type cluster algebras are associated with the.
Yeah, amplifiers online.
Sorry. Sorry. What? Sorry. What was the comment? Sorry, I didn't hear the comment there. Okay. Secondly, there's a huge amount of beautiful things about surface cluster algebras, and if I had another 5 hours, I would love to tell you all about them. For example, just by drawing these pictures, just by drawing a picture and drawing some arcs and so on, and drawing whatever your initial triangulation was, there's ways of reading off the G vectors and so on purely from drawing pictures. So it's really, there's very beautiful, there's lots of extra structure that can help in the case of surface cluster algebras relative to the generic case. Sorry, let me plug in my laptop. But I won't have time to tell you about them in detail. Really, what I want to do is work through one simple example, so you see what the new ideas are. There are really a number of new ideas that go into thinking about this, and I want to tell you what and it's all in progress, but I want to tell you about what some of them look like. And I guess the final thing that I wanted to say, maybe I'll say one thing because we might use it every now and then. There's one beautiful fact, which is that you can interpret mutations in the following way. So if you have any two sort of arcs in this picture, that if you have two arcs that cross, whatever they do anywhere else, the mutation relation just says that the product of these two variables, so there's an arc here and it goes and it does something somewhere else, there's another arc there, it does something else. The mutation relation just says that the product of these two variables is given by uncrossing them in the two ways. So these are sort of famous in many contexts, known as skein relations. So this is a useful thing to keep in mind. I'll do an example in a second. Okay. Okay. So all right. So now what I'm going to do in this lecture is focus on a class of examples that already have all loop information in them. Actually, have quite a lot of all loop information in them, but which are easy enough that I can describe what's going on. Then I'll focus on one very simple example. But the class of examples that I'll talk about, and they missing one important feature of complexity, but they have many of the new features that we have to deal with. And this is going to be a surface which is an annulus. You can call it APQ. So it's a surface that has Q things on the inside, Q boundary points on the inside, and P points on the outside. Okay. Now, what does this have to do with loop diagrams? Well, for example, this includes all the triangulations of these surfaces, include infinite classes of actually the most complicated Feynman diagrams. So let's look at, for example, so let's say we have something at 3 loops. Well, just imagine any triangulation here that forces these 3 to talk to each other. That means in the Feynman diagram language, it would have something like this. Okay, every loop is forced to talk to everyone else, and then they can do whatever else is going on. whatever else is going on later, whatever tree thing is, whatever else is happening. The fact that these three are forced to talk to each other means, as far as the triangulation is concerned, they might as well, these loop points might as well just live on the inside of an annulus here. Okay. So, and there are other classes of diagrams that are accounted for in this way as well. But I just want to just focus on these as a special case. They have, as you see, they have all loop information in them. It's possible to do two loops systematically for any n, but I prefer to talk about this example that also has all loop information in, and also allows me to do everything in a relatively self-contained way. So I don't have to tell you about a few of the new things that they have to talk about when you talk about the algebra with actual punctures in here. Here there is no puncture. I just have this internal annulus with the ordinary boundary points on it. When there are actually punctures, there are some extra issues to experts. You have to talk about tagged and untagged arcs and so on. And I don't want to talk about that. That's besides the essential point here. Okay, so let me just go back then. So we're going to try to understand these cluster algebras. Okay, we're going to try to understand these cluster algebras and see whether there's anything like the polytopes we're talking about. I mean, again, what's the idea? We want to see in this space what's the canvas now? What is the canvas now? The canvas now is I have points on the outside. They're labeled by little I. Points on the inside may be labeled by capital I. And my canvas is I have x little ij's, but these x little ij's can go from like here to there, for example. But note they can also go around. Sorry, I want to go to the same one. So x little ij is not necessarily equal to x little ji anymore. So I similarly have the x capital I capital J's, not necessarily equal to x capital J capital I. So I have those variables, and then I have the more interesting ones, where I have the more interesting ones where you start from one boundary and you end up at the other, and then you can wind around any number of times you like. Okay, so you can call these xii with some winding, right? So there's infinitely many of these guys. There's finitely many of the other ones. But that's our canvas. And again, we have to ask the same question. Is there a question in that space whose answer gives rise to what? It gives rise to sums over triangulations of the surface, first of all, that should somehow know about, maybe give a geometry, a polytope whose vertices are the triangulations of the surface, which we interpret as Feynman diagrams, but which tell us why it's not infinite, because we don't have that infinity in the physics. So somehow we have to be able to compactify this space, even though the G vectors keep on going forever. They don't cover all of space. They miss directions. They miss special directions and so on. The goal is to somehow find a question we can ask in this kinematic space that gives us an answer that's finite, that sort of compactifies this whole structure, and which gives us one copy, which gives us the same number of copies of every Feynman diagram. So it makes sense to add them all up. We get a projective form. We pull back to a subspace, and we get all plus ones. All of that stuff. We want all the same stuff to happen, but we have to somehow confront this issue of the infinity. Okay. All right. So that's our goal. Okay. So let me begin. Sorry, guys. I'm trying to get rid of. Okay. Let's start with the simplest example. Just A11. Okay, so here let's begin. So I just have 1 point on the boundary. We have one point on each boundary, and so here is a triangulation. This one and this one. So I'll call this arc A0 and this one A1 because it winds around once. And it's a pretty degenerate triangulation, but it is indeed a triangulation of the surface. And you can easily convince yourself, I won't do it for you, it's a good exercise for you to do, that the algebra is, that the quiver is actually two arrows, A0 to A1. Okay. Now that was one of the examples that we talked about before as far as the G-vectors go. We'll come back to the picture of the G-vectors in a second, but let me do something a little bit more simple, a picture we didn't really draw before, but I want to draw a picture of the compatibilities. In other words, I just want to draw all the cluster variables and just connect them if they are compatible with each other. Okay, so they can occur in a cluster together. Okay, so this is not like the Polytope, where we connect, here the things that I'm connecting are cluster variables, not clusters, just cluster variables. I just want to denote who's compatible with who. So that's a really simple picture here, where A0 is compatible with A1, then A1 is compatible with A2, A2 is compatible with A3. It's just this infinite chain. Okay, nothing much going on. Okay, so that's the picture of who's compatible with who. But we see that, for example, A0 is not compatible with A2. These guys are not compatible, and in fact, there's a mutation between them. Okay, so that's the first mutation we would do. If I mutated A0, then I would get to A2 with two arrows going the other way. Okay, and obviously, as I mutate, I'm just going to get these quivers going back and forth forever. Now, we also talked before about what the picture of the G-vectors are. And let me remind you what it looked like in this case. It looked like this was, if I started with A0, so this is the G-vector for A0 and A1, then the next one was like -1, 2, -2, 3 on one side. Let me draw the G-vectors in red here. And then on the other side, got longer and longer like this again. And they asymptoted, and they asymptote to this special line, which I'll call delta is -1, 1. So let me denote this little vector there. Delta is -1, 1. So there's clearly something special about this line delta, this G-vector delta. And in fact, the G-vector delta is associated with a very important variable in the surface. But it's a variable that's not a cluster variable. Okay? So if I draw this surface, the cluster variables, which we see in triangulations, are things that start from one end and go to the other. So we can have this one, we can wind around more. But there's another obvious variable, which is just this loop, delta. Okay? Now, even though it's not a cluster variable, we can express this guy in terms of cluster variables. There's a natural way of expressing it in terms of cluster variables, because we can solve for this guy using those Skene relations. Let's see how it works. So let's say delta. So this is delta, and this is A0. So I want to look at the product of delta and A0. Well, the Skene relations tell me when I take the product of delta and A0, one contribution is when I take this and I reconnect these arcs like that. So what do I get? When I get that, what I see is an arc that winds around one way. The one that went around the other way I call +1. This arc that's winding around the other way is A-1. And then, of course, I get the other contribution from, had I done the Skene relations, and I close them up the other way. So if I open them up this way, oh, sorry, I did the same one again. No, I did the other. Then I get A+1. So you see, A0 is so delta is A-1 plus A+1 over A0. And I can solve for, let's say, A-1 in terms of A0 and A1 just using ordinary mutations. So finally, there's a formula for delta is A1 over A0 plus A0 over A1 plus 1 over A0 A1. And from this picture, it should be obvious that this is also equal to AN plus 1 over AN plus AN over AN plus 1 for any n. Okay, plus 1 over AN A1. 1 over AN plus 1. Okay, so this is delta. It has the same formula in any cluster, and it's obvious. It's because it's this totally, winding invariant guy that just that winds around like that. Now, you remember I gave you this way of determining what the B vector is. In this case, the B matrix I told you is 0, 2, minus 2, 0. And so you can take this expression. We can take that expression and decide who the smallest of those guys is, right? So A1 over A0 would be, if this is A0 and A1, this guy would be minus 1, minus 1, 1. We'd have 1, minus 1, and we'd have minus 1, minus 1. Okay, and the rule for the G vector always is to find whichever one of these guys is smallest with respect to the what we said, that if any other guy can be written in terms of the smallest guy plus a positive combination of the columns of the B matrix. And so you can clearly see that that guy in this case, so the G vector for delta is indeed minus 1, 1. And the rest of them can be and the rest of them can be written in terms of this guy plus positive linear combination of the columns of the B matrix. Okay, so there is something special about this direction. This direction that's missing is not a random direction. Okay, so this accumulation that we're seeing, it has a purpose in mind. Okay, but let's go back to our picture and just think for a second practically what we're trying to do. What we want to do, in this case, we're looking for a two-dimensional polytope. So really just a two-dimensional polygon. And we want the normal vectors of this polygon to be the G vectors. And our complaint is that if we do what we successfully did before, sorry, I'm drawing it badly, that it won't work, right? Because we take this guy, so this cone is associated with one vertex of the polygon. This is associated with another one. That's associated with another one, and it just keeps on going forever. So we don't get something finite. But you can say, well, screw it. Who cares? I mean, why don't I just declare? Oops. Sorry, guys. I don't know why everything is just one moment. My whole computer is okay, here we are. Okay. We can just say, screw it, who cares? Why don't I just take these, for example, I'll just stop here. I'll just stop here. Here's a G vector, there's one, maybe here's another one, here's one, here's one. Let me just stop here. Let me just say, these vectors are going to be the normal vectors of some polygon. Clearly, I can do it. Clearly, there is some polygon that has these as the normal vectors to its sides. Why don't I just do that? And I should also say before getting to that, in this case, we can also we can start to apply the philosophy that we had before where we walk. Because this is a quiver, again, it just looks like a tree. So as I walk, if I start with A0 and A1, then I'll get some variable, maybe I'll call them X's, just to remind myself they're not the actual cluster variables. Capital X0, capital X1. Then I'd have capital X2 plus capital X0 minus capital X1 equals some constant. And I'd keep going. X3 plus X1 minus X2 equals some constant prime, and so on. Okay, so I can do this, And the difficulty is, as we said before, it doesn't end. But I can do it if I start, for example, and just walk in this direction. If I walk starting at x0 and I just keep increasing, then I would start with this upper quadrant, x0 and x1, and then I would have to be on the right side of that, and right side of that, right side of that, right side of that, and it just does not stop. Okay, so I can do this walking, but it doesn't stop. But then why don't we just why do we care so much? Why not just take some of these G vectors and just call it a day? Just say, look, these already give me something. You know, let me just take these. It's true, this is a cluster cone. This is a cluster cone. This is a cluster cone. That's a cluster cone. This is not a cluster cone. Not good. Not a good cluster cone. Cluster things don't like this. But screw cluster things. Who cares? We can just make it as some cone. It's going to define some vertex of our polygon. Why don't we just do that? And there are many reasons not to do it. But one that's a good guiding, one that's a good guide is, even if we do this, and in this kind of trivial case it works and it gives us a polygon, it will not have the magical property that if we take and we can get a projective form, that much is really easy when you have any polygon, but it will not have the magic property that there is a subspace where all the signs become +1. And remember, that property had to do with the remarkable fact about the, sorry, apologies. Sorry, guys, just give me one moment. Okay. Okay.
Everything all right, Nima?
Yeah, everything's okay. It's just my computer seems to be overheating. That yeah, this will not have this magic property. If you remember, this property is a consequence of the fact that the determinant of the G vectors in the cones, if I take the two G vectors in the cone, that determinant is ±1. And that will not be true here. So let's just see sort of explicitly if we do a simple dumb example. So if I do,
we don't see anything.
Oh, I'm sorry. Sorry. Can you see now? Okay, good. So if we do this example, so let's say that we decide that these are the G vectors that we want to keep. Then that determinant is 1 because, I mean, so what are these explicitly? So this is like 1 0 0 1, and then -1 2, and then -1 0, and 0 -1. So this determinant. So this was an honest cluster cone, and that determinant is 1. Good. This was an honest cluster cone, and that determinant is 1. Good. This is not an honest cluster cone, and the determinant is 2. So that's how we pay. When we do something arbitrary and stupid, you pay because the magic goes away. And so that's why we can't just do this idiot thing. It's true. It's a completely idiot thing that you can take all of the G vectors, if you take enough of them, Of course, if you take enough of them, they do. If I just take the collection of all of them, they span the whole space. They could, in principle, be the facets of some polytope, but they will not have these miraculous properties of, amongst other things, of having all the determinants equal to 1. Again, having all the determinants equal to 1, in this two-dimensional example, it's pretty simple. I mean, it's not that amazing. In higher dimensions, it's incredibly non-trivial that it's possible to find a collection of vectors associated with the cones in such a way that all the determinants are plus or minus 1. So we don't want to do this dumb thing. So that's why we don't want to just trunk it. Okay, but there is kind of a natural thing we can do. In this very simple case, there's a natural thing we can do, and then we're going to port this to the higher cases. So let's imagine that we keep going on one side, and we're going to stop somewhere. I mean, I'm not really drawing it to scale, but we're going to stop at some a plus m. Okay, and so let me say beforehand we have some a plus m with a m minus 1, a m minus 2, and so on. Here is delta. And then similarly on the other side. So this was a0, a1. Here we have a minus 1, a minus 2. And then similarly here, we're going to stop at a minus n. And then here it's a minus n plus 1. All right. So sorry, the picture is drawn pretty badly. So imagine that as we go along, and we actually saw here that when we solve our mutation relations, I should have mentioned this earlier, when we solve, we say we have a0 plus a2 minus 2a1 is equal to a constant, and a1 plus a3 minus 2a2 equals constant prime, and so on. So these formulas are going to give me a formula for any variable in terms of something a0 plus something a1, and these coefficients are going to be the g vectors in this case. Okay, and so just from the picture, it's manifest that as I walk forward to more positive values, for example, then I get that am plus 1 is equal to am plus delta. And then as I walk backwards, this is for m greater than or equal to 0. As I walk backwards, it's also true that a negative m negative 1, in other words, making it more negative, is a negative m, again, plus delta, not minus delta, plus delta. We see that in this picture, right? As I keep going in this direction, I keep adding something in the direction of delta. Similarly, I'm going the other way here. I'm adding something in the direction of delta. Okay, so okay, that's all fine. Now, what is the problem? The problem is that naively, as I'm doing my mutations, a0 is mutating to a2, a1 is mutating to a3. Okay, that's why it seems like I have to keep on going forever. There's nothing I can do about it. But there is an obvious thing that occurs to you when you look at this picture, which is, well, let's say I want to stop somewhere. I don't want to keep going forever. I want to stop at this am and at that a minus n. Now, what is my problem? My problem is, how am I supposed to, where is a minus 1 supposed to go? This is my first problem. A minus 1 was hopping over this guy before to go to an even longer thing there, but I've decided to stop, so I'm not going to have that guy anymore. Okay? So what can I do? Well, there is a very natural thing I can do. I can say that a minus 1 actually has a relation with delta. And the relation is the one that we've just actually written down. Okay, the relation is saying exactly what I just erased, but let me just write it again. I can say that that a minus 1, am minus 1 has a relation not with am plus 1, but a relation with delta. So delta is like the mutation partner for am minus 1. And the relation is just that this is equal to am. Okay. Similarly, on the other side, I can say that a minus n minus 1 has a relation with delta and is given by a minus n. So you see, it looks like delta can sort of be the mutation partner for both am minus 1 as well as an plus 1, without forcing me to keep adding guys infinitely together. But there's something else I need. Where is AM going to go? So AM also doesn't have someone that it can go to. Similarly, A minus N, well, the only thing they can possibly do is to go to each other. In order for that to be true, it had better be that there is a relationship between them, that their G vectors satisfy a relationship. And the beautiful thing is they do. The relationship is that AM plus A minus N is actually a multiple of delta. N plus M, I forget, maybe there's some number here, times delta. So we see that if we only stick with the world of cluster variables, there's no way we can compactify this space and make something finite in a natural way. But if we see that we're allowed to add delta, then delta can act as a mutation partner for the people who need one. And we also have an interesting relationship between the cluster variables at the two ends, at the two extreme ends. The positive and the negative cluster variables also satisfy a relation. Now, this is non-trivial. It's not, I mean, in this case, we can very easily verify that it's true, but it's interesting that there is some kind of relationship between the G vectors, which involves just delta on the right-hand side. Another beautiful thing that you can check is that all the determinants involving, all the determinants here, all these determinants were of the cones were 1, but also this determinant is 1 and this determinant is 1. So the determinants involving delta are all 1. And so we have we've accomplished what we wanted in this very simple case of a polygon. Here is the picture. If I summarize the picture, we start, for example, we can start from the initial cluster, and we kind of walk forward. Okay, so this is a sort of positive winding, and naively we keep going forever, but we stop somewhere, and then there's something that comes at it from the negative winding direction. And so we can think of the walking that we're doing is that we are walking in this direction, time evolving in this direction, but instead of going forever, at some point we stop. And there are relations involving the last guys here with delta that allow me to glue this end onto that end, and then to keep walking. So, if you like, beforehand, we had a picture of, in all of our previous story, we had a sort of a single space-time. Here, qualitatively, we have, and in somewhat more detail, we have two space-times. We have a space-time associated with the walk in the positive winding direction. We have another space-time associated with the walk to the negative direction. In this case, it's such a tiny one-dimensional example that calling it this kinematic space of space-time is really overkill. But I just want to put it in the language of the things that we're talking about before. Is that there is the natural time evolution from walking on one side, natural time evolution from walking on the other side, and there's a remarkably the delta, this kind of canonical variable that's not a cluster variable, that's in the direction of this asymptote that all the G vectors are asymptoting to, is what's needed in order to allow them to connect to each other. Okay? So that's the story for A11. So let me finish this discussion by at least sketching the story for A21. Okay, so now more generic and interesting things start happening. In my talk next week, I will talk in more detail about what happens in APQ in general, where there's still further things to discuss. But let's just talk about A21. Okay, so what is the surface in this case? So let's get acquainted with this cluster algebra and with the surface. So here I have 2 points on the outside and 1 point on the inside. You could think about this as certain two-loop bubble diagrams, if you like. But again, we're only drawing triangulations of Well, I'm talking about in the language of triangulation of surface. So what are my kind of cluster variables? Well, again, I have the variables that can go from here. I could call that A0. I will call this one A1. Winds around once, and also I have the guys from the bottom here. So I'll call this one B1. It starts from the bottom, and it also sort of winding around here. And if it went around more, I'd call it B2, B3. If it went around this way, I'd call it B0. If it went around the other way first, I'd call it B0, and so on. Okay. So that's the surface. Let's actually look at the quiver associated with this surface. So again, I'll leave this as a little exercise for you. It's extremely simple again, but I'll just tell you what the quiver looks like. So if this is A0, A1, and B1, the quiver looks like this. So this is, so we mentioned this quiver before as an example. Okay, so this is A0, A1, and B1. Okay. Okay, let's just get some idea of what some of the mutations look like. For instance, what happens if I mutate at what happens if I mutate at A0? Okay, if I mutate at A0, well, I know what happens in the quiver. Okay, if I mutate at the A0, I'm going to get something new here, a new variable. Now we're going to figure out what its name is. Okay, but I just reversed the orientation of these arrows. So this is still B1 and A1, and I have something new here. So I have to tell you who this new guy is. But let's go to the picture to see what's supposed to happen. That means I delete A0. And now there's a new arc that I get to fit in this picture to replace A0 to give me a triangulation, and you can see who it is. It's this guy. So already you see these very swirly pictures that you have to draw. So who is that guy? That new guy is what we would call, if this one was B1, this winds around one more time, so this one's called B2. Okay? So over here, I would have B2. And so on. So you can see that if I keep mutating like this, I get a whole set of things that mutate to each other. And in fact, here's a picture of compatibilities. So I would start with, let's say, A0 and A1 and B1 that are all compatible. And then I see, so there's a picture that looks like this. And we'll keep filling it in. But A0 can mutate to B2. So it's not compatible with B2, but A1, B1, and B2 are compatible. That's just what we saw up here. A1, B1, and B2 are compatible. And so the picture keeps on going like this. So then I have A2, A3, B3, B4, and backwards as well. Okay. So this is a picture. This is just a picture to indicate so that we see in one place what all the cluster variables are. Actually, we don't have all of them yet, but we also just see who is compatible with who. Okay, so we just have these triangles going back and forth in all directions. Okay, but there's something else that we could do. Let me go back to the original quiver. Let me go back. So we're just trying to get an idea of what the cluster variables look like. Who's compatible with who, and so on, just so we get a complete picture of what all these variables are. So let me go back. And so and now let's see what happens if I mutated B1. So that means that I erase this guy. When I mutate, I erase this guy. And now I have to put in an arc that I get to put in now that I didn't put in before that can complete the picture. And that's this one. So that's a variable we didn't talk about before. But okay, that's one other interesting cluster variable. We'll call this one U, and the analogous on the bottom side we'll call D. Obviously, from here you can see U and D are not compatible with each other because they intersect each other. Okay, but when we mutate at B1, we're going to get U instead. And what is the new quiver that we get? Well, it's we talked about this before. We reverse the orientations, and then this guy gets a doubled arrow. And now this guy is U. And then we have something analogous on the other side for D. So let me summarize what the picture looks like. The picture looks like this. This is the picture of, again, who's compatible with who. If the variables are connected by an edge in this picture, it means that they're compatible with each other. Okay. The picture looks like this. So I have like A0, A1, A2, B1, B2, B3. B0, A minus 1, and so on. And then up here, I have
the original two lines have to be parallel?
No, the parallel means nothing here. I mean, I'm just drawing them. This is just a shorthand for me to be able to draw them quickly. Okay, so this is just indicating that A1, B2, and A2 are compatible with each other. B2, A2, and A3. So anything that's connected is compatible. Anything that's not is not compatible. And I can mutate, for example, from A0 to B2. Meanwhile, U is compatible with all of the A's, and D is compatible with all the B's. And again, that's sort of obvious from the picture. U is this big loop that comes down from here. So obviously, any A at all does not intersect U. So it's totally fine and compatible with the U. Let's actually stare at this picture for a little bit, just to recognize some things. So, for instance, we know that we just saw that the cluster involving U looks like it has an A, like an A0 and an A1, for example, with this doubled arrow. Okay, so just this double arrow part means that inside here is exactly the A11 that we're talking about before. In other words, if I just ignore U, just the cluster algebra associated with A0 and A1 is just that infinite chain we were talking about before. So not surprisingly, there's that infinite chain is associated with an A11. Here's another infinite chain associated with the B. All right. Now maybe some more fun ones. Like let's look at the initial cluster. Let's say A0, B1. I keep drawing it wrong. Anyway, A0, A1, B1. Okay. You see. In here, we have all kinds of interesting subalgebras. For example, there's a subalgebra just involving that just looks like an A2. So what does that mean? That means that we should be able to find, because we can do if I do mutations where I never touch A1, if I just touch these guys, then I should see a whole A2, and that means that I should see 5 clusters because we had a pentagon. So where's that? That's here. So if I just leave A0 alone, here is a cluster. You see, any triangle in this picture is a cluster because everyone is compatible. I should have said in the beginning, this space is 3-dimensional. We have 3 cluster variables. So there's one cluster. Here's another one involving A0. Here's another one. Here's another one. Here's another one. So there's a whole pentagon there. Those 5 clusters are the 5 clusters of the A2 cluster algebra. Okay, and so on. So there are pentagons in this picture. There are these infinite chains, and they all reflect the underlying. Well, anyway, they all very simply reflect the structure of the algebra. All right. So now what I want to do is tell you what the picture of the G vectors looks like, and this is where things get interesting. Now this picture is three-dimensional, right? Because the G vectors are three-dimensional cluster algebra. So the G vectors are three-dimensional, but because what I just care about are the cones made from the G vectors, I can basically do a two-dimensional projection of this picture. In other words, maybe this is what the G vectors really look like in 3 dimensions, but I just care about what the rays look like that come out of these points. And so I'm going to imagine intersecting them with some plane. If I intersect them with this plane, then every G vector is going to look like some point on this plane. But things that I care about, like here's a cluster cone, here's a cluster cone, that will just show up as triangles in this picture. So everything that I care about, as far as whether things fit snugly and so on and so forth, will be captured by this picture. What will not be captured by this picture is whether the determinants are 1 or -1, so that we'll have to check separately. But a lot of the geometry is nicely captured by this two-dimensional picture. So let me tell you what the two-dimensional picture ends up looking like. Okay. So this is what it looks like. So first of all, it should be obvious from what I was saying that, remember that the sort of picture is that the G vectors are mostly covering space. So there's no way that if I do one of these intersections with a plane that I'm going to be capturing all the G vectors. So I'm going to ignore some of the early ones. I'm going to ignore some of the early G vectors down here, and I'm only going to plot late enough G vectors that are all captured on this two-dimensional by intersection with this two-dimensional plane. Okay, but anyway, here's what the picture looks like. Like, let's say that I just stop by the time I get to A2 and B3. Okay, so then this is what the picture looks like. So here's D, B3, and A2, and U, and A-1, and B0. Okay? So these are those guys as G vectors, and they have various they're part of cones with other variables, but the other variables aren't captured in this picture yet. I mean, they're outside this sort of they're outside this rectangle I'm drawing. So let me actually sort of keep going to fill it in a little bit. Well, first let me tell you some interesting things about the geometry. So let me draw this. Oops, hold on. I think my laptop is really complaining. Sorry. Let me draw this. Let me draw these dashed diagonal lines here. So first, a cool thing is that delta is smack in the middle of this picture. Okay. So delta has some important, as you would expect, has some privileged role to play in this picture. It's smack in the middle of this picture. And as I mentioned, as we go to higher and higher cluster variables, as in the more and more wound cluster variables, we just keep adding delta. So that means that in this two-dimensional picture, they're just moving in the direction of delta. And here's actually what the picture looks like. So let me draw some pictures. You'll see the pattern. So I'll draw that line. And this intersection point is actually A3. Let me also draw this vertical line. Sorry, guys, my computer now just froze entirely. Just 1 second. Let's try this. Okay, that's better. Okay. So let me draw this vertical line as well. So delta is actually on all these intersection of all these lines. So here's a minus 1. Okay, so so the line B3U intersecting this determines A3, and then that straight line determines B4, and so on. On this side, this was B0, so this is B minus 1. You see everything as you keep winding in is just approaching delta, and this guy is A minus 2, and so on. So what I want you to see from this picture is we see quite vividly the whole idea that there are G-vector cones and they tile and all of that, and also what's going on and that they're converging onto this direction delta. So all of the triangles in this picture, like this triangle is a G-vector cone between A2, A3, and B2. That's a legal cluster. This is a G-vector cone. Everything involving U on this side and the A's, these are all, that's a cone. This is a cone on this side. This is a, these are cones involving the D's and the B's. This is a cone on this side. This is a cone on this side. These are cones between the B's and the A's on this side. So you see, I go in one more step and I get more G vectors. I don't know what is going on here. I'm very sorry. I think my computer is complaining about, now what happened? Okay, good, sorry. So as I keep going in, I get more G vectors, more cones, but they're covering more of space, but there's still something missing. And if I keep going more, I'll just get a more and more, I'll get a picture that starts converging in to something smaller and smaller surrounding delta as I continue. Okay. Note something quite beautiful, which is that D, U, and delta lie on a line in this picture, and that line separates on one side the positive winding from the negative winding. So once again, if we wanted to, and let me actually go back and say what we could try to do, we could start from our initial cluster. So let's say we decided to start from this initial cluster, A0, A1, B1. And if we started from this initial cluster, it doesn't have any loops, it's acyclic. So I could walk, let's say forward. There's nothing wrong with walking forward. I would walk forever. But there's a few funny things. So I'd have to walk forward in this direction. I'd have to walk backwards, starting from the negative guys on the other side. So I have two separate walks. But one, again, the usual funny thing is that they don't stop. A new funny thing is, of course, there's some variables I don't even see when I walk. I don't see this U and this D at all when I do this walk. So that's something we didn't encounter in our previous trivial case. And yet we see that there's something kind of natural, that in the full world of the G vectors, I have a kind of a positive walk side, a negative walk side, and the variables that are missing are really lying on a plane that separate the, are lying on a line that separate the two of them. If you remember that this is a two-dimensional projection of a three-dimensional picture, it means I have one whole set of G vectors from the winding variables on one side of a plane, another set on the other side of a plane, and that U and D and delta lie on this plane. All right, so let me keep going with the picture of the G vectors. I'll draw it not as a quadrilateral, just for, I'll just draw it as a rectangle for convenience. So let's say that we've gone up to some point now, up to some A capital N. So the picture looks like this. It's much skinnier than what we drew before, but anyway, it still always looks like this. We have some A negative M at one end and a B negative M plus 1. Okay, so we've stopped at this point and we have delta in the middle. And as I said, delta lies on the intersection of all of these lines. So delta is a super special point in here. Okay. Okay, so now we can try to do exactly the same. We can try to do exactly the same. We can try to do exactly the same game as we did before. We keep going. We keep mutating until we get to these end guys. When I get to these end guys, I have the usual problem that the same as the problem that we saw before. But now let me draw it in this picture. So I'd have A0, A1, A2, let's say, and let's say A minus 1, and then B1, B2, B3, B0. Say I stopped here. Then when I'm doing my walk, I'm mutating from A0 to B2, then from B1 to A2, and so on. And then I have the trouble that B2 doesn't go anywhere. Where does B2 go? So where does this penultimate B go? And that has the same answer as before. That B2 would have wanted to go inside to a G vector inside this rectangle, but instead of having it go to that G vector, we're just going to have it go to delta. In other words, the relation that we'll write down for B2 is just that B2 plus delta is equal to B3. Or more generally, in the case where I've stopped at Bn plus 1, we'll write down this relation that Bn plus delta is equal to Bn plus 1. Okay, so that takes care of where Bn is supposed to go, and we have the analog on the other side. We'd have some A negative m plus 1 plus delta equals A negative m on the other side. So that takes care of what we're supposed to do with where these guys want to mutate to. We also have all the mutations involving U and D. And for example, there are mutations that look like D plus AN equals BN plus 1, or D plus A minus M equals B minus M, and similarly mutations involving U. Now, some of these things we see in this picture. For example, here we can see that D plus AN is equal to Bn plus 1, because Bn plus 1 is on the midpoint of these guys. And so similarly here. But once again, some of the mutations we don't see. Again, they involve partners that would want to go inside this cone. But once again, remarkably, delta is doing quadruple duty to making all these things work. Instead, we just write down, there is a relation of exactly this sort. We just have to remember that we write down that Bm plus 1 is equal to Bm plus delta. And we see those relations in this rectangle too. I draw the rectangle again. We geometrically see these relations because here's delta. So the relation says that we can have that D plus AM is equal to Bm minus 1 plus delta. Okay. So just that the midpoint of Bm minus 1 and delta is the same as the midpoint of D and A minus 1. So the relation is that D plus A minus M is equal. So the one that this dA relation on the positive side we see on the boundary of the rectangle. The one that we don't see does exist, but it involves delta. So D plus A minus M is equal to B minus M plus 1 plus delta. And similarly for U, we have U plus B and plus 1 up here is equal to AN plus delta. Right, so that solves the problem as we saw before, but now in a slightly more intricate setting. That solves the problem for what to do with the fact that the variables, as we walk along, don't have someone that they can mutate to. Delta is their mutation partner. They can all mutate to a delta, and these relations are correct, and they allow that to happen. Finally, we have to ask the question, though, as we saw before, something has to allow me to connect the variables from the positive winding side to the negative winding side. The thing that we saw before that had a relation of the form of the A of the negative winding plus the A of the positive winding. And that's the really interesting thing here, is that we have exactly the same kind of relation here. And it has exactly the same character, that there is a non-trivial relation between the positive and the negative winding variables that involves delta. Okay? And that so that relation is actually of the form that AM plus A minus N is equal to U plus some multiple of delta. And similarly, BM plus 1 plus B minus N is D plus the same multiple of delta. I should say that in all of these cases, the relations have exactly the same flavor that we had before, that the variables on the right-hand side of the relation are compatible with the sum of the two variables that we have on the left-hand side. The only exception is that delta is allowed to be slotted in everywhere. Delta is allowed to be slotted in everywhere and is sort of friends with everybody. But once you do that, we can have legal relations that first tell us who we're mutating to. All the guys that are missing partners they can mutate to can actually mutate to delta. In the language of Feynman diagrams, they would say there's a funny propagator that will be called, every diagram goes somewhere, except they're not separate variables. It'll all be called delta. So we still have a picture, and we'll see, we have a picture of a polytope, all of whose vertices are triangulations of the surface, but there's a finite number of them. And the novelty is that some of the vertices all involve delta. So delta is doing multiple duty to be the mutation partners for everyone. Okay, so that's it. There's a few other novelties in the story, but I'll leave that for a more detailed discussion in my Zoomplitudes talk on Wednesday. But if I sort of summarize what's going on, but the summary is that we now have a set of relations. We have a walking, a time evolution up. We have a time evolution that stops somewhere. We have a time evolution in one direction. We have one space-time that we stop somewhere. We have another space-time that we stop somewhere. And then there is this U and D and delta that allows us to glue these two space-times together to make a larger one. Now in this case, again,
Nima?
Yes.
Just to be clear, you're not writing at the moment, right?
Yes. No. I'm not. Can you see me?
No, we see a blank page.
That's what happens. Oh, sorry. That's the problem. I lost the video. Sorry, I was gesticulating wildly at the screen. Yeah. Okay. 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 Good. Yeah. So let me say it again. So we have so we evolve in one direction.
No, we still see the blank page.
Sorry, you don't see me?
No. Oh, I'm sorry. I do see you in a different window.
Oh, okay. All right. So yeah. So let me just say. So well, okay. Maybe I can write as well. So in fact, I can draw the picture like this. So we can even draw a little picture of something like a space-time. It's such a small example that it doesn't look like much to begin with, but just so you get an idea. So here is a little just with the A and B variables. Remember, these A and B variables were the ones that are winding and the ones that we're sort of doing time evolution in. And here is an amusing little picture. So Okay, so this is supposed to be thought of just like the meshes in the space-time picture that we drew before. Notice that this picture has an identification. It's a really tiny cylinder because I have A1 on this side and A1 on that side. But anyway, I'm supposed to draw every one of these meshes as a little Gauss's law. So this is the Gauss's law, A1 plus B1 minus A0 minus A2. A1 plus B1 minus A0 minus B2. That's one of the mutations. You already see something slightly nice, that this mutation, A1 plus the A0 plus A2 is equal to 2A1. And that was one of the mutations that we get from the A11 subalgebra. So we see that not all mutations are created equal. That's what I was mentioning before. There are these basic elementary mutations that are the pixels of the space-time, and the more complicated ones are built out of linear combinations of them. It's just, this is such a small example where there are really just two types. There is this basic one, and there's a slightly more complicated one, which is a combination of the previous ones. But anyway, we can think of this as a tiny little strip of a space-time in this tiny example, and we can keep sort of evolving in this direction forever. But then we have to decide to stop somewhere. And so the picture is that if I sort of just put it on its side, I sort of keep going. These are the A's and the B's, so I keep going, and I stop at some point. I can also walk the other way. But here in the middle, we have U and D and delta. And U and D and delta first talk to A and B on one side separately from the other side. So that's the phenomenon that A and B, the people that they have to mutate to, can be found, that they can mutate to a delta. And separately than that, this allows us to write relations that directly connect the two sides to each other as well. So, so we have a picture of a kinematical space-time here. Again, this is very tiny in these cases, so it doesn't seem worth calling it that. But I'll at least tell you what the generic story appears to be for APQ, where you do see something that looks like a space-time. So, and we walk in this direction. We stop. We connect via this UD delta world to the other negative winding sector that allows us to keep walking. Okay. And this actually works. You can explicitly see in this simple case, there's a three-dimensional polytope. I just want to show you a picture of what the three-dimensional polytope looks like. So this is what the analog of the ADHY polytope looks like for this 8-to-1 example. So it's a little bit fancy. As you see, it has this hexagonal face that's being illustrated at the top here. That hexagonal face is reflecting the fact that delta, that face is associated with the delta variable.
Hey, Nima.
Yes.
Are you showing us a slide?
I am. Oops, sorry, 1 second. Oh, there we go. Can you see now? All right.
Yeah, we can see it.
Huh?
Wait.
Yeah, we see it.
Let's see.
I don't
see this. Yeah, I don't either. That's. Oh, hold on. I see. I see the problem. One second. All right. Yeah, this is some Zoom annoyance sometimes. Sorry. Okay. Here we go. Can you see now? Good.
Yeah.
All right. Okay. So here's a picture of the three-dimensional polytope, actually associated with like walking as little as possible. So literally in this picture. So here we'd start with like A0, B1, A2, and then we just keep walking until A2 and B3 on one side, and A minus 1 and B0 on the other side. So there's a U, there's D, and there's delta here, and delta talks to everyone. Okay, so delta talks to everyone on these ends. So there's a facet here. That facet corresponds to the delta variable, and so the fact that delta is compatible with 6 variables here means that we have to see a hexagon. So there's always a hexagon in this picture, no matter how much we walk, because at the end, this delta is compatible with 6 guys. So you see it's kind of a fancy looking polytope, but how do we get this polytope? Exactly from the rules that I told you. We begin with the initial cluster, we walk, we write the relations, the mesh constants are, the constants that we see in the relations are positive. We walk to the ends, we write the relations at the end, which are the ones that mutate the guys to their missing partners. Those ones we write involving delta. And then we write the relations that connect a negative winding variable to a positive winding variable. And doing that gives us self-consistently this polytope. And quite beautifully, and for very good general reasons, all the determinants are 1. So all of the determinants also involving all of the cones involving delta are 1. So this really does everything that we want for this example. It gives us a polytope. All the vertices are labeled by triangulations of the surface, but we stop somewhere. And all the ones that involve a missing variable, delta is the stand-in for that missing variable. I'll just sketch and then we'll just end. I'll just sketch what the picture is. I'll sketch what the picture is in general for APQ. So the picture for APQ is quite a bit richer. So for APQ in general, we have the part which involves walking. The part that involves walking involves the arcs that go from one boundary to the other, and that part looks like a cylinder. So it's like you have a trunk. It looks like a cylinder, and you keep on evolving for some time. If I unwrap that cylinder, so here's the picture, and this is the first winding sector, the next winding sector. I can keep going. I can wind however much I want, and then I have to stop somewhere. Now, if I just think naively, again, about what my kinematic spaces are, then I have the space of these xii's. So if these are I and I, these are the things that we're seeing in this walk. Okay? So that's what's captured by this cylinder. But I also have xij's and xij's, little I and capital Ij's, for reasons very similar to what we saw with our story for the icosahedron. Each one of these is themselves a space-time. Each one of these themselves is associated with, in this case, a sort of a P by P or a Q by Q space-time that's itself a cylinder, which I have unwrapped. And so all of these space-times glue to each other in the following interesting way. And this is just a sort of a cartoon of the picture. So here is the cylinder that we get just by time evolution, by walking in one direction. And this guy talks to, I'm going to draw this kind of in the following sketchy way. Okay, so we have one space-time which corresponds to the positive winding region. We evolve. Then in here we have, on one side we have all of the xij's, and on the other side we have all the little xij's. And I've drawn it this way. I mean, they're just copied. They're exactly the same things on this side. It's just saying the xij's can talk to these guys, and they can also talk to the other guys. Okay, they can talk to both the winding sectors. Okay, so here's the xij. So there's a kind of a that was supposed to look like a square. I've drawn it kind of a little bit badly, but each one of these is their own space-time, actually their own cylinder that I've unfolded as well. And I've drawn it this way to emphasize, and delta is in the middle here. I've drawn it to emphasize that there are relations that tie these guys to one side, that tie these guys to the other side, and delta allows us to go between the positive winding and the negative winding world. And really, I think, to me, fascinatingly, the direction of time evolution is like this. It's like you time evolve in this direction, and then in these space-times, you time evolve in the orthogonal direction, and you come out the other end, and you keep time evolving in this way. So in these pictures, there are sort of multiple kinds of things that look like space-times, and each one has its own picture of fundamental relations, and they glue to each other in such a way that the whole thing works. And a crucial star of the whole story is this object delta. All right, so that's all I'll say about this subject. I'll say more about where we are and more details in my talk at the Zoomplitudes. But what I want to emphasize is that, so first, there is a way of dealing with this infinity problem in this case in a natural way, and it's not a hack. The way is actually suggested by the structure of the G vectors in the cluster algebra itself. We see from the cluster algebra that there's more going on than just the G vectors, that delta is this important object in town, and delta is exactly what allows us to give a finite compactification of this whole space and get a polytope that does all the things for this example that the ordinary finite type polytopes do for the cases that we know and love. And it's interesting that the sort of basic idea that of all the relations there are between G vectors in the cluster algebra, there are special ones which are the kind of pixels of the space-time, and that you have to use those to build the rest of them. And in addition to that, these sort of new relations that tie different sectors together, they all exist. We couldn't have invented them if they didn't. They all exist. They're part of the structure of the cluster algebra, and that allows us to make sense of infinite classes of all loop processes, of all loop diagrams. As I said, these sort of simple ones where the internal loops all talk to each other so that you get these annuli. There's really further new things that start happening when you have genuinely 3 loops and above, and when you have things beyond the planar limit. I won't say anything about that here. I will say something about it in my talk at Zoomplitudes. All right. Okay. So that's it for this. I think we are approaching the what are we approaching now? The 10-hour mark. What are we approaching?
Yes, Nima, 10 hours.
10 hours. Okay. Well, what do you want to do now? We can. I'm happy. I mean, we might be hitting saturation. I think we're down to around 53 people. I wanted to also talk about the non-perturbative geometries for n equals 4 super Yang mills, but I'm not sure whether people are up for it or not. Ultimately, well, we could just stop. We could just have a general discussion. Anything you guys want is fine by me.
It's up to you.
Yeah.
Why don't we leave it up to you?
One option is to take a longer break, like 15, 20 minutes, so that people who want to leave can do so without feeling ashamed.
Okay.
And then I don't know, or we could stop. How are you feeling?
No, I mean, I'm feeling fine. I'm totally fine. Yeah, I mean, I think the last topic is probably another. I think it's another hour or so. Maybe less. But on the other hand, if people want, I don't know what people want. I mean, if they want, there's been an overload of different kinds of material. So people would rather. I don't know what the fraction of people left is who are all experts. Probably everyone's an expert now. I don't know. Anyway, okay. Look, why don't we take a 10-minute break? 15-minute break is fine, and then come back. And whoever wants to hear the rest of that story, we can talk about it. Or if people would rather do something else and just have general discussion, that's fine by me too.